Hello, everybody. We will wait a minute for everybody to get here, and we are going to start at 4 p.m. And 1 minute. Okay, we can start. So, hello everybody. Let me introduce myself. My name is Tanguy Guénic, and I am a project and project manager at Skylabs. So, I'm happy to be in front of you today in order to present you a short webinar regarding the orbital angular momentum, and especially how do you twist light and generate OAM beams. So if you have any questions during this presentation, a dedicated space is available at the bottom right side. And Pujian, head of the product marketing team, is with me today and will sort out your question. And I will answer them at the end of the presentation. So let's start. So before get started, I will tell you a few words about Skylabs. So who we are a deep tech company, and Skylabs developed a few years ago unique patented technology, which is the MPLC as multiplane light conversion. And more generally, we are experts in beam shaping. We are now 50 employees, and we are in capacity to develop, manufacture, and sell innovative optical components. And we are located at Rennes in France. What we call exactly with beam shaping. It's possible to play with several properties of the light, like the power, the wavelength, the polarization, and the phase. And at Skylabs, we allow the addition of a new degree of freedom thanks to beam shaping, which is the shape of the light. This has a lot of area of application, and we developed a range of products. Let me present them. First, we have the Canuda product, which is specialized into the improvement of laser industrial cutting lasers. And we have after the Aruna product. Aruna proposes to improve existing legacy network. Tilba is for the free space satellite laser communications. And personally, I'm in charge of the Proteus product and customs application. Custom is not a product. It's relative to specific development for application in defense, automotive, aeronautics, or biomedical, for example. About Proteus, Proteus today is the state of the art of the MPLC, and it is the product to make space division multiplexing. I'm going to explain what is it after. So, but this presentation is linked to this product. So, firstly, today I want to spend some time in order to explain you what is the OIM of a light beam, what are its properties, and why they are so interesting. After, what are the different ways to generate an OIM today in the market. I'm going to explain after what is the solution proposed by Skylabs to generate this kind of waves. And finally, I will present you some application where we use our solution to generate them. So what is an OIM and the orbital angular momentum? The angular momentum is something related to rotation. Any rotation objects can produce angular momentum. For the light, we can consider two forms of angular momentum. The first one is the spin carried by photon particles. It's produced by local rotation of electrical and magnetic field vectors. For the circular polarized light, this rotation produces spin of light. The second one is more tricky to explain because it's related to the phase of the light. Indeed, the phase front of this kind of waves forms a sort of helical structure where the light locally propagates along helical trajectories. And the spiral trajectory produces the orbital angular momentum. A famous analogy is the Earth-Sun one. In this movement, the spin of the Earth is the rotation of the Earth on itself, and the OAM of the Earth is analog to the rotation of the Earth around the Sun. So the OAMs have an additional component that appears when writing a solution to the propagation equation. It is this one inside the blue square, where L represents the topological charges, which is in fact the number of helices or spiral that we can find in the phase front of this kind of wave. On the bottom right side, you can see 3 phase fronts with 3 different topological charges in order to see how it looks like. So now, what are the properties of an OAM and why they are so interesting? The main property is as OAM wave have a quantified quantity, its number of spirals, we can consider this L number as a bit of information. It means that you have another way to transport information because this number is completely independent of the wavelength, the time, the frequency, or the polarization. And if we can convert the information into OAM, we can improve a lot the bandwidth of the future telecommunication networks. Other interesting application is the ability to resist to the turbulence phenomena. Indeed, many people attribute them these properties, and that give interesting perspective for free space laser communications applications. At the end of the presentation today, I will give you some example of works on this subject. A last example concerns the manipulation of small objects. Experiments have been carried out in order to set in motion an object illuminated by an OAM, and these results are interesting with potential applications in the medical fields for the localization of microscopic elements of interest, which become in rotation under the field of these waves. So now let me explain about the generator available today on the market. And the first one, the cylindrical lenses. This was the first method to generate OAM waves. It consists in transforming an input Hermite Gaussian beam into Lerger-Gauss mode by using 2 cylindrical lenses. Each series of AG modes with several successive phase transformation can form LG mode with OAM. It is a mathematical and optical decomposition which permit to have excellent results as soon as we have a perfect alignment and a good AG mode generator. Unfortunately, that's why also this method is particularly difficult to implement. The second one is the spiral faceplate. A light beam can acquire an OAM by passing through a spiral faceplate or variable thickness. This spiral faceplate has the ability to create a vortex beam whose shape and characteristics depends on the shape of the faceplate. The higher the topological charge needs to be, the greater the difference in I between the beginning and the end of the helix will be. The spiral faceplate has high conversion efficiency and can be used with high power laser. But it has also the limit that it can generate a single mode only, and it needs tight precision requirements, especially for high order modes. phase holograms. Using a network of diffraction, it's possible to generate OAM by the regular alternation of constructive and destructive interferences. This interferences is called an hologram, and the representation of a phase hologram printed on a transparent medium has the appearance of a kind of a fork. The quality of the OAM formed by this type of element is correct when we have to generate low-order OAMs. But this beam quality tends to decrease strongly for larger or higher order OAMs. This is because the OAM order is directly proportional to the frequency of the interferences, and the limit is a way to print very fine, high-resolute holograms. Moreover, from an energetic point of view, this type of array, once illuminated, generates 3 output beams, of which only one is useful to us. Metamaterials. Metamaterials is a new and really promising technology. It's a composite material with electromagnetic properties that we cannot find in a natural material. Research has shown the ability of an ultra-thin metamaterial to change the phase of an incident beam to achieve OAM. Researchers have proved the ability to generate order modes up to 20. However, work on metamaterials is relatively new, and it's still an immature technology. And this is not today a component on the shelf. Spatial light modulator now, composed of a pixelized matrix of liquid crystals. The molecule composing it can be programmed to modify the parameters of the incident beam, including its phase, to create a twisted beam. The spatial light modulator can have the behavior of both a spiral and fork phase hologram to form OAMs with different configuration. Unfortunately, this type of optical element, because of its structure, is not compatible with high-power lasers. And in addition, as you need a computer to control it, it's not a passive component. So to finish the cuplates component, cuplates, like spatial light modulators, are composed of an anisotropic material which can transform a circularly polarized Gaussian beam into a twisted beam carrying an OAM. The advantages of cuplates are the high conversion efficiencies, and in addition, they do not deflect the incident beam compared to holographic components, and they can be used with a wide frequency range. Unfortunately, cuplates can only generate, most of the time, only one type of mode per model. So now it's time to explain our solution to generate OAM. So our solution is the MPLC as a multiplane light conversion. It's a technology patented by Skylabs in 2010. And MPLC is reflective technology and passive optical process whose principle is derived from quantum optics. I can show you a short video in order to make the explanation easier. So with the succession of phase plates and free space propagation, we have the ability to transform any kind of Gaussian beams in whatever we want, as soon as it's a unitary transformation. So a unitary basis into another unitary basis. If you want more complex shape and multiple beams, mathematically, they always have a solution to modify this shape with more phase plates and Fourier transformation. In fact, Fourier transformation is free space propagation. If you have to do that in transmission, there is a risk to have a lot of insertion losses. That's why Skylabs decided to have the device in reflection. So we realize a unique texture surface, a unique faceplate, and the free space propagation is done with the help of only one mirror. And we can have much more input. We can combine them or divide them in two separate channels. So we have several optical fiber at the input. We modify each input with the faceplates and the free space propagation until a multimode fiber, where we are doing spatial multiplexing. Of course, with a similar product on the other side, we can demux the information in order to retrieve your initial input signal. You can also modify the fibered element to free space optic, and you can have a lot of different configurations which correspond to different applications. So Proteus is created from this techno, where we have inserted the MPLC block inside a kind of box in order to be used easily for everyone. So I come back to my presentation. So these are cool examples about shapes that we can realize. On the left side, it's a single mode transformation with only one fibered input. And on the right side, it's multi-mode transformation with more inputs. Now, let me compare all the presented technology to the MPLC. But before, I would like to ask a short question about the OEM generator you have already used or you used to work with. Yes, you should see a kind of survey. And please answer it before continuing the presentation. It's just to have an idea about the using proportion of generator you use today. Okay, maybe you have finished. Okay, so the results are shared. Most of you are using MPLC. I hope that you will be more to use it at the end of this presentation. So thanks again for this survey. It's always interesting to have this feedback, to know what kind of generator people use, and for the rest of the presentation too. Okay. So to compare all this technology, we choose 5 different criteria. The first one is, can high order mode be generated with good beam quality? MPLC can generate any kind of OEM mode with a high purity value. We already produce a OEM generator up to 7 modes with 95% of purity. 7 mode, in fact, is not a limit. MPLC can generate up to 45 modes in fiber optics, and 200 modes in free space have been demonstrated. Is it a passive system? Most of all this technology are passive, except the spatial light modulator, and MPLC is a passive system. Is the technology compatible with high power? MPLC, because of its reflective design, is compatible with really high powers. The highest power achieved in our component today was 16 kilowatt for material processing applications. Can multiple modes be generated with this technology? MPLC can generate multiple OEM orders with only one component. And the final question, is the technology capable of doing space division multiplexing? So what is this first? Space division multiplexing is a technology that permits to improve the bandwidth of telecommunication networks. So by using several shapes of light simultaneously, in a multi-mode fiber or in free space, the input beam are made collinear and they become independent channel of information. And today, Proteus is the only commercial solution that offers space division multiplexing with OAM. So in order to summary what we said in the last slide with the 5 different criteria, we can check that the MPLC meets all the requirements. And if we want to summarize, we have integrated our MPLC inside a box to propose a unique product based on our patented technology and to create a Proteus product. With Proteus, we have a record number of mods, up to 45 mods inside an optical fiber. We have a high optical performance, low insertion losses, record crosstalk between mods. We are flexible. It means that we can work with a wide range of wavelengths, all types of input and output. It can be a free space or fiber. And we are compatible with high power laser. So it's a perfect tool for MUX and DMUX OIM information. And today, I repeat, this is the only commercial solution that offer space division multiplexing with OIM. Now, I would like to finish the presentation with some real case studies. Our case studies have been carried out uniquely in the context of future telecommunication researches. For the first example, I would like to share with you a research experiment realized by the University of Southern California and the team of Alan Wilner. Alan Wilner and his team are convinced of the superiority of the OIM mods and their better propagation in the atmosphere. They realized a real free space optic laser communication between a ground station and a drone. He used only 2 OAM beams with different topological charges in order to multiplex the information to transmit much more information. Today, it's not the state of the art regarding the bandwidth of the OAM propagation in the air. However, we obtain really promising results. So for 100 meter transmission between a ground station and a drone in motion, we obtain a speed of transmission around 80 gigabits per second. The second example is really interesting too. It's still a telecommunication experiment from the University of Southern California. It's still close to the free space optical laser communication, but in this case, they decided to use OAM beam as a quantum key distribution. We know that the free space optical laser communication is a safer link because it's more difficult to intercept. Indeed, you need to be perfectly in front of the signal if you want to read it. Moreover, if you use a quantum key to protect the information, it means that if you try to read it, you corrupt it, and the information becomes impossible to be read. And in that way, they used a pair of Proteus in order to MUX and DMUX OAM mods to generate this key. About the performances, for 850 meters free space bidirectional communication, we MUX 2 OAM mods per direction for communication speed close to 20 megabits per second per channel, and a really good quantum symbol error rate. So to finish, I wanted to share you an example of experiment where the use of Proteus could be very useful. To introduce other possibilities, this is an example of application with ring core fiber, and the interest of the ring core fiber is that we do not have to use a MIMO if you want to MUX informations. Different research teams have done several experiments to transmit different OAM orders by a spatial light modulator within a ring core fiber optic. And the use of Proteus equipment would allow this type of experiment by offering space division multiplexing with a low insertion loss, with a low crosstalk, and with it, users can easily retry all the experiment value quickly using a pair of Proteus. And so it's just to conclude by making it easy to generate OIM mods from our multiplexer. Today, Skylabs hope to participate to the researches on this primitive physics domain, which is the OIM. So from my side, I finish my presentation. So thank you for your attention. And now it's time to answer to your question. Okay. You mean for the use case? This one? I should assume that is this one. It was an experiment realized 4 years ago, and today, yes, we propose a really better OEM generation. But yes, we guarantee today 95% of purity. Where is the question? Answer my following. So, is it possible to produce helical beam? Also, can we use the light source? Yes, of course. The aim of the MPLC is not to produce OAM, but this is the aim of the presentation. We can produce really good OAM, and of course we can use this kind of things in imaging science. But if you want to, yes, if you have more questions, feel free to write me after this presentation. I will be happy to answer them, especially if you have some application in imaging science, for example. And yes, do not hesitate to write me. So thanks for your attention, and yes, have a nice day. Bye.